So last class we ended up at this point here where when we compiled the code, we ended up returning a pointer or the address of a local variable. So if I go ahead and I compile my program, I'll get the warning that the function returns the address of the local variable. And as we saw, we ran this in a different compiler online. So we ran this here, and we got a seg fault. Whereas running it in on the Corey machine, if I go ahead and I run it, it seemed to work fine. But as we said, you cannot rely on that. You can't have one program work on one machine and not work on another machine, right? That's called undefined behavior. So I told you that instead of putting it by default on the stack, like we do here, like a local variable in a function, we're going to put it in this other memory space that doesn't go away when we exit a function. And that memory space is called the heap. So in order to use the heap, I have to import a library, like everything else in C, right? We need to import things we need to use. And the library is stdlib.h. It stands for the standard library.h. Okay. So how do we go ahead and use the heap? Well, the heap is a pool of memory that we can ask space from. So for example, our student here will take 8 bytes in memory. How do I know that? How do I know this? Well, I have this 2 integers, and each integer takes 4 bytes. So I have 8 bytes. So I need to request 8 bytes of memory on the heap. So I will call this function. I will say, hey, memory allocate on the heap, or allocate memory on the heap. This function is called malloc. It asks for memory to be put on the heap, and it says how many bytes of memory do you want? 8 bytes of memory. Okay, and malloc will give me the address of where those 8 bytes of memory are what the address is of those 8 bytes. And that's where I'm going to put my student. Now, since malloc returns the location of memory, this is a pointer. So I have to store the address in a pointer, or I have to remember the address where on the heap those 8 bytes are. Since I'm going to be storing a student in those 8 bytes on the heap, I will say student t star, and I'll say I can just call the same thing. I can just say temp student. Well, in this case, I'll name it ptemp student because it's a pointer. And then one slight adjustment here that we have to do is malloc returns a generic address, or what is called a void address. But we're going to be storing student pointers or student addresses there. So all I have to do here is cast the return type from malloc. So I just have to say student t star, and this is a cast. It will cast the generic address that malloc returns into a student address. Now you say, well, Vito, how did you know this was 8 bytes? What if my structure was pretty large, or I didn't know how many bytes it was? No problem at all. There is a special function in C. It's called sizeof, and it will give you the size of a variable or the size of a structure. So in this case, I'll say sizeof student t. Please note that I'm not putting a star here. I need the size of the structure, not the size of a student address. I need the size of the actual student structure. So no star there. And now this is just a pointer to a memory address that's on the heap that will live or will stay active until we formally or explicitly delete that memory address. So now I can get rid of my temp student here, and I can work with my pointer variable. So I just have to say ptemp student, and just get rid of the ampersand. And as you already know, no dots but arrows when we deal with addresses. And now I can get rid of the ampersand here, and let's go ahead and give this a shot. Let's save. Okay. We'll go here. We'll say GCC example1.c. Seems like we have an error. Oh, I didn't rename my variable everywhere. So this should be ptemp student, and this should be ptemp student. Okay, let's give that another shot. Perfect. So as you can see, the addresses are the same because it's the same address that I'm returning. So I'm returning a copy of the address, and the address is just a number, so I'm returning a copy of that number, which is still the same number. There's a small issue now. My program has a leak. Okay, let me just get rid of this print statement here, and we will address the leak. So how do I know that my program has a leak? Well, every malloc call needs to be matched with free, which frees the mallocated memory. Let's say I didn't know this, and I wanted to find out if my program has any leaks. There's this special program on the Curry machines, not just on the Curry machines, but you can set it up on your machine too. It's called Valgrind. And if I run Valgrind with my executable, it will perform some analysis. It will say, hey, you definitely lost 16 bytes of memory in 2 blocks. So it says total heap usage, 2 allocations, right? Those are, I called make student twice, so I called malloc twice, and I didn't free anything. So I have a leak here of 16 bytes. If I wanted to get more information, I can run Valgrind with the leak check full flag. So I'll say leak check equals full. I can run that again, and it actually kind of tries to tell me where I've allocated the memory, so I know how to deallocate it. So it says, hey, there's 8 bytes in make student, and then there's another 8 bytes in make student. So that's how you can kind of try to figure out where where your leaks might be coming from. Okay, I'm going to clear the screen here. So what do I do now? Well, I have to write a function that will free the student. So one could write something like this, for example. I could say, before I exit, I could say free ps1, and then I'll say free ps2. So now the memory will be freed, and I will not have any memory leaks. The problem with memory leaks is if you have a lot of memory leaks, and over time you will run out of memory, and your program will crash. Okay, so you try to avoid the memory leaks. Okay, so let's go ahead and try this again. So let's say GCC example1.c a.out. Everything's still working good. Let's go ahead and now run Valgrind again. It says, hey, all heap blocks were freed, no leaks are possible, 2 allocations and 2 frees. Perfect. Now, you just have to be careful not to use, bring this up a little bit. you have to be careful not to use these pointers after you free them, or don't double free them. So for example, if I try to do something like print student PS1 after I freed it, this is undefined behavior, so it might work, it might not work. So let's go ahead and run it and see what will happen. So it seemed that it worked, but this might not be the case. I might end up getting a segmentation fault. Let's go ahead and try to actually run this in the online compiler. So we'll say cat example1.c. I'll take the code. Okay. Come here. Let's go ahead and run it again. It didn't crash. It says 0, But again, as I said, this is undefined behavior, and sometimes it might crash, other times it might not crash, depending on when the memory is exactly freed. So undefined behavior. Right? So we shouldn't be doing anything with the pointer after it's being freed. All right. So I hope this made sense. The other thing that you have to be careful, let me clear the screen here, is you have to be careful not to have null pointer exceptions, because that will give you a segmentation fault, or the program will crash. So what am I saying? For example, I'm saying this. Somebody might do something like this, right? Or you might have a null pointer, So every time before you use a pointer, especially in functions when you take it as an argument, you have to make sure that the pointer that you're dealing with is not null. So something along these lines, right? We'll say if a student is null, and we'll just return. This is very similar to what we did in Java, where we say objects.require not null, and it will pass be a student, right? This is what we would normally do in Java. The other thing you have to be careful is malloc might fail if you don't have enough memory. So the return type could be null. So we have to check that. We'll say, hey, if ptemp student is null, we'll return null. So I don't want to access ptemp student if it's null. All right. And also, I have to be careful not to free a null pointer. So I have to come here, and if I say if ps1 doesn't equal null, we're going to go ahead and free ps1. So you see how this could become a little bit cumbersome, but this is C, so you have to do these things. And then I'll free both of them. Another good habit is after you free a pointer to set it equal to null. So it's always a good idea after you free the pointer to say ps1 equals null, to set it to null. So therefore you kind of if somebody ends up using ps1 after I've freed it, their program will crash 100% of the time, as opposed to crashing some of the time. Okay, and we're going to go ahead and do the same thing for the other free functions. So we'll say we'll free it, and then we'll say ps2 equals null. Okay, it might actually be easier to write a function that will free and set the pointer to null, but in this case we're not going to do it. All right, so essentially in Java, as you've heard, everything is a reference, or everything is passed by reference. Remember when we remove the reference to a private variable, that's where usually the bugs happen, right? It's not a copy. We're returning an actual reference to a private variable. So you can kind of see that objects in Java, are actually just, in a way, pointers. But Java kind of hides that away from you. And it has a garbage collector. It means that when you're done using an object, it will call free for you. So you don't have to do it. Right? So those are the advantages of Java. Right? But C is bare bones, and you have to do these things by yourself. So you have to, there's no garbage collector to do it for you. All right, so this is the heap. So I'll stop the video at this point. And the next point, we're going to see how we can implement a singly linked list, okay, in C using nodes and pointers. And you're going to see a contrast between what you did as a list in Fundis2, where you used recursion, and the C way of the pointer way of implementing a singly linked list. Okay, I hope this made sense, and I'll see you in the next video. Thank you.